Hi and welcome to yet another lesson where we're doing vectors for Maths 1503 or linear algebra. So, a vector is basically a quantity with both magnitude and direction. I have a few examples. So, if you have something like 5 kilometers or a magnitude with a quantity with a unit that is a scalar, and the word east here in the next example basically tells us the direction. So we have both magnitude and direction. So this is now a vector, right? And when we're talking about vectors, we're basically going to be talking about the second example that I made for you. So a vector basically can be represented in several ways. The first one being the arrow notation. So you having that or this little arrow here on top of the alphabet basically tells you that that's an arrow and a vector, and that's basically the notation that we're going to use quite often. Secondly, we have the column vector. So you would have that arrow notation and the column vector like that. And mind you, this is not really a matrix. A matrix would be if you had V on its own. But right now you have V with that arrow, which tells us that this is not a matrix, but a vector. This basically tells us where X and Y are and would give us information. And from that information, we can then draw a resultant vector, right? So for example, just gonna make use of this space. So if you have Cartesian plane like that, and you told that X is here by 3 and Y is also here by 3, you connecting the dots would be you drawing up a resultant vector. Okay. Then we have the ordered pair form, which you would have something like that. So these things make you, or instead of having obviously the curly brackets that we usually have, in this case, when you're representing a vector, if you don't want to do the ordered pair form, you would have, sorry, if you wouldn't want to do the column form, you would have this ordered form where you have arrow brackets like that. The last one is the positional vector, where we use this I and this J, right, with the caps there. So you having this cap is now you saying this is a unit vector inside a positional vector. Once we start with unit vectors, I will basically also come back to this and do a whole summary why we have unit vectors inside positional vectors, right? Where I, in this case, would be that, and J would be that. And then I basically said again, the cup makes it a unit vector. Positional vectors, you have to understand, right? It's more like your X and Y intersect. So it's more like you're starting from the origin. So if you think of what J is or what J makes, let me try to draw it here. So you have this Cartesian plane, right? And it's saying to you that J is the same as J is the same as 0 is to 1, 0 is to 1, and you know that that means X is 0 and Y is 1, so you have it somewhere here, right? And then with your I, it's the opposite, where X is 1 and Y is 0. So you would have X somewhere here. Let me use a different color. So this would be your Y and that would be your X, right? If you look at this, I is being multiplied to 3, right? So you'd go 3 units extended, and then J is multiplied by 4, so you'd extend that to up to 4 units. and your resultant vector would be there. So can you see why they're saying they're starting from the origin? That's because they're starting from where x is 0 and it's a positional vector. Remember, you have i's and j's, where I will tell you where to start in the y-intercept. And then now this also tells you that vectors can be scalar multiplied, meaning they can extend. When they extend, they don't change direction. They just move in the same direction, just a longer version of that direction. And I have a little side note here that these vectors, basically the positional vectors, do things like character positioning when you're thinking of gaming, or camera position. Obviously, when you're thinking of how to lay your camera sometimes has this line. I don't know how to show it, but there's a line to show you is your phone is straight or positioned straight, or sometimes you can have grid positions to know where you want to be. So sometimes you can have object positions. All of these are basically stored in positional vectors. When you're doing computing, you would understand what I'm talking about. So now we're going to talk about the difference between points and vectors, which is quite a big misconception when you come to linear algebra, because they are quite the same, right? But also different. A point basically describes where the location is. For example, if you have that, this means go 3 units x and 4 units y, right? And then a vector basically describes the movement instead of where the location is, right? So if you have this vector AB, this would mean go from A to B, right? For example, if you have a graph like this and you're told that A is a point, 3 is to 4, A is basically where 4 is and where 3 is. Now, if they say to you, I thought I had it. If they say to you, find or draw up the vector BA, obviously, if your A is here, and you know that you're supposed to move from B to A, your B would be somewhere there, and you would go like that, right? And that's basically what your thing is. I made a side note here. So vector BA, in this case, BA is where the point is and where the head is, right? So A would be where the head is, and B would be where the tail is, if you understand me. So I drew up a little vector to show you what I mean. So the head is represented with that arrow, and the tail is where you start, right? So BA would be where x is 3 and where y is 4. So you'd move like that in that direction. So you'd move all the way as x becomes 3 and as y becomes 4, you keep moving. Like when drawing functions, you'd use an arrow to indicate where the function is going. I made an example here. So you'd have something like that to show that the function is going up in this direction and is going down in that direction. Okay, let's talk about magnitude. Obviously, if a vector is a quantity with both magnitude and direction, we have been talking about direction, so now I think it's time that we talk about the magnitude, right? So the magnitude of the vector is simply the size or the length of an arrow, and we use Pythagoras or Pythagoras or the length formula to determine the magnitude. I made a side note here of what Pythagoras looks like and what the length formula would look like. Obviously, this is quite where geometry meets with the vectors. Right. So if obviously you're using Pythagoras, you want your triangle or whatever vector that you're forming to be in a triangle form, and that should be in a right angle, right? To find the resultant vector, of course. And we typically use this formula when the graph starts from the origin. Like I showed you what positional vectors are. You would want to use it obviously when you start from the position, because that would formulate a triangle, right? So I have an example here, and you're told to find OP, right? So you're given this, and then you're told to find OP. You wouldn't obviously know where P is, but O is by just looking at it. So if obviously you know that with vectors you have to go from O to P, you would basically have P being somewhere, O being there, and you have that as your vector because now you have a head. If you didn't have a head, that means you don't have a vector. Finding OP, I'm going to have one method on the right and another method on the left. So this would be equal to 3, where x is 3, plus 4 of the y squared. And this would give us 9 plus 16. That's 25. And this is 5 units. Right? And then for the length formula, when it's quite long, obviously, so you'd have x1 minus x2. Let's make x2 3. So x3, x2 minus x1 squared plus, as you can see, it's quite useless using this formula if you're starting from the origin, because you're basically just going to have that and that, which means you're doing now Pythagoras, right? So you'd have 25, which this is 5 units. Obviously, we quite do have to show what the magnitude is represented by, because you can't just say the magnitude is OP. This basically tells us that the vector is OP, not the magnitude. So you basically, for the magnitude, you would have to have two things. If you have only one, that means you're finding the determinant of OP. And to show that you're finding the magnitude, you'd want to have two lines in each side. So this was basically the magnitude of OP, right? The magnitude of the vector OP. So you're showing that it's the magnitude of a vector, because if it was just OP, you're basically finding the magnitude of a scalar. Okay, let's move to parallel vectors and slopes, which obviously also this is where geometry meets vectors. So suppose, for example, or consider that you are given a vector A as that and vector B as that. If you think of it, notice that A is twice vector B. To go from B to A, you have to multiply by 2, and this side as well, you still have to multiply by 2, right? So, or if you think of it in this sense, if A is this long, B is that long. And can you see that they're heading to the same direction? That means vectors can have slopes because they can be parallel, all right? I made a little side note. This tells us that A is twice vector B, so they point in the same direction, or in the exact same direction rather, and thus both have vectors lie on the same line, right? So whether you elongate A more, you're still gonna lie in the same line as B. And because we've learned that vectors can be parallel, this obviously means they can have slope, which we would use this formula to calculate slope, right? So they can ask you to prove that A and B have the same slope. So you'd have to calculate the slope of A first and then calculate the slope of the vector B. And then if they're equal, you proved obviously that they are equal. So linking unit vectors to slopes. So in other words, actually, instead of finding slope using this, we use unit vectors. And I did touch base on what unit vectors are in the first part of this recording. So the formula for unit vectors is basically u with a cup like that, and the vector over the magnitude of that vector. So, which you can always manipulate the formula to find different things. If you're given both unit vector and the vector, you can find the magnitude of the vector. If you're given this and this, you can find what the vector is. Or if you're given both of these, you can find what the unit vector is. Made a little example here. So they're saying to us, if P is equals to this and its slope is equal to 2, and also they gave us the magnitude, which is square root of 45, and then they're saying to us we must find the unit vector P. Remember, the cup means unit vector. Oh, I didn't write it. So using the formula, you would have P cup is equal to, the vector is 3 is to 6 over the magnitude was given to us, which is 45, right? So all of this, you can solve it further and have it as 45, and then you have 3 is to 6. I would basically want you guys to stop here for you to see a pattern. So notice that like we were doing with A and B when we were looking at parallel vectors, what does this tell you? It tells you that the unit vector is always parallel to the, in this case, vector P. So unit vector P is always equal to its vector. If you look at this, you have vector P here on the side, and then you have a scalar, which was the direction, or sorry, the magnitude. You have a scalar on the side, and then you have the exact same vector P. Remember when we had A being 2 times vector B, you had a scalar and the vector A, right? And the vector B, but it's kind of the same thing. But this basically tells you what a unit vector does, right? I'm going to summarize it. If you want to, you can solve it further and have 3 over square root of 45 here, and 6 over square root of 45, right? And this basically is what a unit vector is. However, I need you to also notice something. If I were to take 6 over square root of 45 multiplied by 3 over square root of, divided by 3 over square root of 45. This is the same as 6 over square root of 45 multiplied by 45 over square root 3. If you were to cancel these two, you would have 6 over 3, and that is 2. Remember what they told us. They said to us that the vector P has a slope of 2. Now look at what a unit vector, the slope of the unit vector now is also equal to 2. What does that tell you? It tells you that a unit vector will always move in the same direction as P and will always be parallel to P, right? And thus have the same slope. In other words, a unit vector is simply a shorter or a longer version of the same arrow whose length has been forced to become 1. So the unit vector, basically the tips I can give you is that the unit vector only changes the length of a vector. So it can either be short or longer, but not the direction. So the direction doesn't change and the slope also does not change. Right? So like I said, it's always forced to be 1. So I need you to on your own, prove that the unit vector, the magnitude of the unit vector here is 1. We're almost done. This is the last bit that we're doing. So vectors between 2 points. So suppose you have A as that and B as that vector. And I drew it for you here. So you'd have A and B. It's always nice to start from the position. Other ways to represent A, you would have A being equal to 2I. I almost said plus. Yeah, but it's plus 1J. Instead of 1J, you can just have J like this, right? So A, in other words, is the same thing as this, or B also, you can represent it like that, right? They're saying to us here, we have to find the magnitude of AB, and obviously we've learned now, because you have 2 points that you're dealing with, you would want to use the length formula. So in this case, you would have 2 minus 7 squared plus 1 minus 5 squared, and that's negative 5 squared plus negative 4 squared, and that's let me see, 21 plus 16, which would give us 41 units. And you don't have to obviously solve the set further, because we don't use calculators for this module. So you basically just want to leave it like that. So here we were finding the magnitude of the vector AB. Remember, we're not going from A to B. In this case, we're finding what the magnitude of the vector AB is. So the whole thing of AB is. And then they're saying to us here, we must find the vector from A to B. So A is here and B ends there. So we must find this whole magnitude of the vector. So that's the area that I kind of did, but I mean this, right? So obviously, if you think of it, listen, just try to listen. If you need to find only this part, you have to take this whole thing minus this little thing here, so that you are left with only that. So think of it in general. If you're finding the vector AB, you basically now doing this. So you're going vector B, so vector B minus vector A, and vector B was given to us as 7:5 minus 2:1. And this basically is obviously when we subtracting or adding in vectors, we do it in corresponding terms. So you're going to go 7 minus 2 and then 5 minus 1. So 7 minus 2 is 5, 5 minus 1 is 4, and that is this vector here that you found. I gave you guys some homework to try. Please do take a screenshot and try this on your own. It's quite everything that we've been doing, except this time I added in that number 3. So, but I think you can try. Just remember everything I've said. I did try my best to have you guys have notes, but that's it for this recording.